In this experiment, the time dependence of current flowing in an RC circuit will be examined. In order to follow the time dependence of the current, we have recorded the real experiment videos. Today, I am going to explain you how you should use these videos to get data. First of all, I want to say that the videos given you runs at 0.1 frames per second. This means that the frequency at which consecutive images called frames appear on a display is 0.1 per second. So the time between each frame is 10 seconds. Secondly, I am going to explain you how to prepare experimental setup for an RC circuit that has a resistor and a capacitor in series. The position 1 of the switch is turned on the charging circuit. Microammeter is used to measure the currents and connected the circuit. Then open terminal of the resistor is connected to neutral position of the switch. Finally, a multimeter is used to measure the voltages between the capacitor. The same setup will be used also for discharging process. This setup can be arranged for discharging process by connecting the position 2 of the switch to one of the slots that has connections with the minus terminal of the power supply. In the first part of this experiment, after choosing an appropriate output, the switch is brought to upper position and simultaneously the video is started to record. The current will reach at its maximum value at this instant, and after that it gradually approaches to zero. During the experiment, all possible values of the current from its initial value to the value close to zero are recorded on video. Since the time difference between the frames can be found out from the video in seconds, and also the pictures in the video shows the values of the current, you can measure the current values corresponding to certain time values by using this video. Let me open a file as an example for you. Please don't forget that the values that I will use in this example are different from the values given in your file. So, you should use the values in your file to prepare your report. The tracker software should be installed on your computer to open experiment files. After opening the file, you can see the frames consecutively by using Step Forward button. At each frame, read and record the reading values of the current I by ammeter and then fill the values in table 2. Let me show you how you will fill in the table. The first current value is 3060 microamperes. Don't forget to record the error values in your measurements. In this measurement, the error, which is the smallest division we can read, is 5 or 10 microamperes. Don't forget to put proper unit over here. Click the Step Forward button to measure the second current value. It's 350 microamperes. Keep recording data until the last frame. Then, to fill out the time column, remember that the time difference between two frames is 10 seconds. Since the video starts at t equals to 0, start with 0 and increase the time t 10 seconds at each row. Then calculate the logarithm of the current value at the time t divided by the current value at the initial, namely ln of I divided by I0, and fill in the last column on the table. After filling in table 2, go to Data Tool window to analyze the data. Click the file and select New tab. Click New column. Enter the column name as time second and click the OK button. Click New column again and name as ln I divided by I0, and then click OK button again. time values should be on the horizontal axis. Now, the time and ln of the I divided by I0 values should be recorded on the table. Zero time value is 0 and the logarithm is also 0. All data should be entered in this way. I've entered and saved this data for you before. Please don't forget that this data is different from yours. After the data entry is finished, click the Analyze section and select the curve fits to plot the baseline. On a standard plot of I versus t, I approaches to zero exponentially. After a time equal to R times C, current I in the RC circuit has decreased to inverse of E, about 0.37. Since the product RC is a measure of how quickly the capacitor charges, we call R times C as the time constant of the RC circuit, as denoted by tau. The time constant of a given RC circuit is the time at which the current in the circuit drops to 37% of its initial value. This happens at the time t equals to R times C seconds. This is hard to visualize or quantify. The better solution is plotting logarithm of I divided by I0 versus t. In this plot, the current will look like a straight line. So, you should select fit name as line. The slope of the baseline gives you the inverse of the time constant. Sign of slope is negative, indicating that current decreases. Calculate the experimental value of the time constant in the charging process by taking the inverse of the slope and record in the table 4. Take the image of the data tool screen of the tracker software this image in the graph part of the template on figure 1. Lastly, calculate the error of the time constant by using this formula in the calculation part of the template. Tau value is the experimentally defined value of tau. Delta I is your uncertainty value in the current measurements. These T and I values are the maximum values in your data table. Whatever the maximum value on the data table T is going to be over here, and whatever the maximum value of I is going to be over here. So once you put these values on the equation, you can calculate delta tau. These steps complete the first part of the experiment. You should do the same procedure for the second part of the experiment, in this case of discharging the capacitor. In this part, you should use the second video, which is recorded as soon as the switch is brought to position 2 after the capacitor is sufficiently charged. After doing the same procedure as you did in the previous case, fill out the table 1 by reading the value of the resistance from the color code and reading the value of the capacitor. And then calculate the theoretical value of the time constant by using the values in the table 1 on the formula tau equals R times C and record your results in table 4. Finally, compare the theoretical value of the time constant with the values you have found from the graph in the discussion part.